Hiya Jack, this is your feedback video for the Circular Motion 2 homework. Okay, so question 1, you needed to label the forces acting on the car in both situations. So well done for labeling the reaction force, although this should equal the weight in this diagram, so that arrow should be a bit longer. You've correctly drawn it here, that's good. However, friction force is not correct in either diagram. The friction force actually acts the opposite way. Think of it like this: friction will try and oppose the motion of the car. The car, if this was a frictionless surface, the car would try and slide that way. The car would slide that way as it goes around the circle. In this diagram, the car would tend to slide up the slope in the absence of friction. The friction is what's stopping it from doing that. It's opposing that attempted sliding motion. Think of it like that. So you want these arrows to point the opposite way. In part 2 here, the possible origins of the centripetal force on the car, right? This isn't the right approach. What they mean is, essentially they're asking you, look at the forces acting on the car. Which forces are providing the resultant force toward the center of the circle, right? Well, if we look at the diagram, let's look at the reaction force first. I've drawn in the vertical here and I've labeled this theta. The reaction force has a component toward the center of the circle. In other words, it has a horizontal component, which would be r sine theta. That is partly what provides the centripetal force. The other thing is, this is your friction. The friction force has a horizontal component, okay, given by, let's call it f sine theta. So it's the sum of those horizontal components of these two forces that give you the centripetal force. So you need to redo this bit here. This calculation is correct. Well done. Next question, you got full marks. Okay, so I'm not going to discuss that. This question here, the van going over the humpback bridge. Okay, I want you to read through this carefully. Okay, it wants you to label the forces acting on the parcel. Okay, on the parcel, not the van, just the parcel that's inside the van. So there's no friction force on the parcel. This here, come on, velocity of the van, that isn't a force. Velocity isn't a force. I think maybe you've meant the driving force of the van, but that's a force that acts on the van. It doesn't act on the parcel. The parcel is at rest relative to the floor of the van. There are only vertical forces acting on it. Okay, so I can't give you the mark for this. This bit here is fine, but I'd like it if you rearranged it to make r the subject of the equation. Okay. This calculation, your method is correct, but this here should be 55 newtons, not 54. Something's gone wrong somewhere. It might be your value of G that you've used. You need to use 9.81. Okay, you've got to use the value in the data sheet. Redo the calculation using that value of G and see if you get 55. Okay, but I can only give you 1 mark for that. Unfortunately, this here isn't right. If the speed of the van increases, then R would not go higher, it would go lower. Now, I'm going to give you a kind of pointer to get you thinking about this the right way. The key thing you need to do is you need to look at the equation that we wrote down here. Reaction force equals mg, which is the weight of the package, minus this term here. This here, the weight of the package, is a fixed number. It's not going to change. The weight of the package is what it is. It doesn't matter how fast the van is going. So think of that as like a constant. But this term here, that is going to change when v gets bigger. In fact, it's going to get bigger, isn't it? So if you think about it, r is the weight minus this term. If this term gets bigger, then the reaction force will be decreased. Okay, so I need you to put that into words here. All right. And finally, question 5. All these calculations are correct. Well done for getting this bit right here. Good work. I'm just going to pause briefly while I read through your answer to this last bit. Okay, Jack, yeah, so I had a look through your answer. There are definitely things that we can add to this, but you've made some very valid points. This is really good. As seen in figure 3, the vertical component of the tension stops it from falling, okay? Its magnitude would be equal to its weight. This is good. That's really good. Due to Newton's first law, you need to kind of expand on this a little bit. You could say that you could say something like, since the ball is not moving vertically, that tells you there must be no resultant force acting on it, which is an example of Newton's first law, maybe. And then this is nice here. There is the centripetal force comes from the horizontal component of the tension. Yeah, good. A couple of things you could add. You could discuss the fact that because the ball's in circular motion, explain why in detail. Why does that mean it's accelerating? So you explain that means it's accelerating. Okay. Then you say, according to Newton's second law, there must be a resultant force acting on it that's causing it to accelerate. That's where you fit in the second law bit. The third law, we'll talk about it in the lesson, but this is pretty good. You haven't mentioned the third law, and you haven't fully discussed. You haven't explained why the ball's accelerating. So this would be worth 3, maybe 4 marks. I'm going to be conservative and give you 3, okay? But as I say, we'll discuss it in the lesson. Okay, if you've got any questions about any of this, just let me know.